Virtual Events Happy Math Hour, weekly interactive math reviews for Math 1314 and Math 1324, presented by Ivechuca, Ruben Carrizales, and Albert Isasi. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come and watch it. Thank you. So now at this time, please mute your mics for best sound experience. Otherwise, the feedback could interfere with the information we'll be sharing today. We're going to post the link to the Math 1324 room. So that's available and you can click there and reach the site. It's not there. And without further information, here are our presenters today.
Everyone. Happy Friday. Can you guys hear me? All right, cool. So today we're going to go ahead and review for exam two. Some of you are getting ready to take exam two either right after spring break or maybe during this weekend, right? If you're taking an online class. And so we'll get started here. And so this exam two will cover sections 2.1 through 2.6. So first, we're going to focus on 2.6 problems. And so here we have a rational function. And these are all the things that they're asking us to find. And so we're going to go through each one. That way at the end, we can graph our rational function. So the first thing is they want us to find the domain. And so in order to find a domain, remember that there's some problems that are going to have exceptions. And so if you have a fraction and it has a variable in the denominator, then that means that there's going to be some numbers that we need to exclude from the domain. And so in order to do that, we could probably just look at what numbers would cause us to have 0 in the denominator. But if you're not sure, then you can set the denominator equal to 0 and solve for x. So if we solve for x, we get x is equal to -3. And so what that means is that -3 cannot be part of the domain. So we're going to go ahead and exclude it from that domain. So the domain is going to be all real numbers except for -3. And so in WebAssign, they give you it's a multiple choice problem. So we would circle that last choice. So for letter B, they want us to find the intercepts. So we'll start with the x-intercept first. We're going to let y equals 0 and solve for x. So we let f of x equal to 0. Then in order to solve for x, I'm going to multiply both sides by x plus 3. And so 0 times x plus 3 is going to be 0. And then x plus 3 multiplied to 1 divided by x plus 3 is going to be 1. So 0 does not equal to 1. That's a false statement. So what that means is that this is going to be, there's no intercept. It does not exist. So we would just enter D and E for our answer. Now to find the y-intercept, then we're going to let x equal to 0. So if x is equal to 0 and we solve for y, then we get 1/3. So when x is 0, we get 1/3. So now we have our x-intercepts. Now we're going to look for the vertical and horizontal asymptotes. And so to do that, let me just review what they are. So vertical asymptote is going to be represented with a dotted line here. And in order to find those vertical asymptotes, we're going to factor the numerator and denominator completely. And then we're going to cancel any like terms. And then once we cancel any like terms, we're going to set the denominator equal to 0 and solve for the variable. Now note that if in step 1, if you do cancel a factor, then what it creates a hole in your graph. Okay. So let's go ahead and find the vertical asymptote for this problem. So if you notice, my numerator is 1, that's already factored, and my denominator is x plus 3, and that's already factored. So we don't have to do anything for step 1. So now we set the denominator equal to 0. So I'm going to subtract 3 on both sides. And so x equals -3 is going to be my vertical asymptote. And so I would represent that with this dotted line. Now for the horizontal asymptotes, they're also represented with a dotted line, but they're going to be horizontal. And there's three situations. The first one is if the degree of the numerator is less than the degree of the denominator, then you automatically have a horizontal asymptote at y equals 0, which is the x-axis. If the degrees are the same, then your horizontal asymptote can be found using the leading coefficient of the numerator divided by the leading coefficient of the denominator. And the last case, if the degree of the numerator is greater than the degree of the denominator, then there's no horizontal asymptote. And if that's the case, then you also want to check if there is any slant asymptotes. And to check for that, that means that the degree of the numerator would have to be one more than the degree of the denominator. So I think later on we'll see an example of that. So back to our problem. So the degree of our numerator is 0 and the degree of our denominator is 1. So the degree of the numerator is less than the degree of the denominator. And so that's going to tell us that y equals 0 is our horizontal asymptote. So far we have our two asymptotes represented with the dotted lines there. And so now if we continue, then we have our x-intercept, which does not exist. We have our y-intercept, and then we found our horizontal asymptotes. But in order to graph this, it's important to plot additional points. And so the additional points that you want to plot, so first let me plot my y-intercept, which is 0 and 1/3 right here. And so the points that you pick, you want to pick points on the right side of the vertical asymptote, and you want to pick points on the left side. That way you know what's happening with the graph. So for this example, I'm going to choose -2 and I'm going to choose +2, just, to get a better idea. So if I put -2 for x, then I end up with 1. And if I put a +2, I end up with 1/5. And then on the left side, I'm going to choose -4 and -5. So if I plug those in, then I get a -1, and -5 is going to give me a -1/2. So if I plot all my points, this is what it looks like. And so if you still need more points, then you can pick as many points as you like. But one of the things that we do know about these asymptotes is that the graph is going to get closer and closer to the asymptote, but it's not going to cross it or touch it. And so we can graph that knowing that this is going to get closer and closer to this vertical asymptote. And then remember that our horizontal asymptote was the x-axis here. And so the graph is getting closer and closer. And then the same would be on this side. And so that would be our answer. But let's try another example here. So again, these are the steps that WebAssign wants us to find. So we'll look at the domain first. I have a fraction with a variable in the denominator. So that means there's some numbers that I cannot use. And so I'm going to set that denominator equal to 0 and solve for x. So I get x equals -3. So my domain is going to be all real numbers except for -3, which is the second option here. And now the intercepts. For the x-intercept, we're going to let y equal 0. Then I'm going to multiply both sides by x plus 3 so that I can get rid of that fraction. And so I have set it up there. And so 0 times x plus 3 is 0. X plus 3 times this fraction would give me a 3x plus 2. I'm going to subtract 2 on both sides. And then I'm going to divide by 3. So my x-intercept is x equals -2/3. Now for the y-intercept, we let x equal 0. So anywhere you see an x, we replace it with 0. And then we simplify. So 3 times 0 is 0, plus 2 is 2. 0 plus 3 is 3. So my y-intercept is 2/3. So that should have said y equals 2/3. So now for the next step, it says to find the asymptotes. So if I look at my numerator, 3x plus 2, that's already factored, and x plus 3 is already factored, so there's nothing for me to do there. I'm going to set my denominator equal to 0, and so x equals -3 will be my vertical asymptote. And so I plot it here with my dotted line. If you use a graphing calculator to check your work, the graphing calculator will not show you this vertical asymptote. And then, so the horizontal asymptote, the degree of the numerator is 1, and the degree of the denominator is also 1. So since the degree of the numerator is equal to the degree of the denominator, then we're going to look at the coefficient. Then we're going to look at the coefficients. So the coefficient for the numerator is 3 divided by the coefficient of the denominator, which is 1. So we get y equals 3. So my horizontal and vertical asymptotes are plotted here. And now we can plot the information we do have. So we have -2/3 and 0, which is somewhere around there. And then 0 and 2/3, somewhere around right there. And let's pick some points. So I'm going to pick some points on the right side and on the left side. So I'm using -2. If I plug in -2, 3 times -2 is -6 plus 2, -4. And so we end up with -4. If I plug in a +2, I end up with 8/5. And then for -4, that's going to give me a 10. And for -5, that gives me a 13/2. So if we plot those additional points, then we're going to have our graph, which is going to go like this and like this. Okay. So again, the important thing is when you choose those additional points, you want to pick points that are on the left side and right side of that vertical asymptote. And we'll do one more of these, and then we'll continue with the rest of the chapter. So here we have the same idea. So let's find the domain first. So the domain here, if I set the denominator equal to 0, I get 0. So my domain is all real numbers except for 0. Next, the x-intercept, we're going to let y equals to 0. So 0 is equal to x squared minus 9 divided by x. I'm going to multiply by x on both sides. And so 0 times x is 0. My x's here will become 1, or they reduce. Some of us like to say they cancel. So we get x squared minus 9. If I solve for x, then I get x squared equals to 9. I can use the square root property, take the square root on both sides. So x is going to be 3. So my x-intercepts would be 3, 0 and -3, 0. For the y-intercept, we're going to let x equal to 0. And so if I put in 0 here, then notice I cannot divide by 0. So what that means is that your y-intercept does not exist. So you would enter D and E as your answer. Okay, so now to find the vertical asymptotes, I always like to factor to make sure that there's nothing I can't cancel. So x squared minus 9 is the same as x minus 3x plus 3. And then we have x on the bottom. I can't cancel anything here, so that's okay. So we set the denominator equal to 0. So 0 is your vertical asymptote. And now for the degree of the numerator is 2. And the degree of the denominator is 1. So this is the third case, right? So the degree of the numerator is greater than the degree of the denominator. So that tells us that we have no horizontal asymptote. So that means that we should check if it has a slant asymptote. So is the degree of the numerator 1 more than the degree of the denominator? So it is, right? So we have a 2 and a 1, so that's 1 more than the degree of the denominator. So that means that we have a slant asymptote. To find the slant asymptote, then I'm going to go ahead and use synthetic division. So I have my x squared is a 1. I don't have an x, so I use 0. And then we have our constant -9. And so here, remember that the number out here would be your k, x minus k, but we don't have a constant, so we use 0. And if we proceed, we have bring down the 1. 1 times 0 is 0. 0 plus 0 is 0. 0 times 0 is 0. And then we get -9. So your quotient that we get from this synthetic division, so this 1 is the coefficient of your x. Since we had x squared, we go 1 less, so it's going to be x. So this quotient is actually going to be your stand asymptote. So we would write it as y is equal to x. So if we were to graph it in a little bit, you'll see what that looks like. So we put everything together. The dotted line here is my slant asymptote, y equals x. I have a x-intercept at -3 and +3, and my y-intercept is at -9. And so I want to plot in some points, or maybe you kind of already know what the graph should behave like. You know it should get closer to the asymptote, but we can also plot in some more points. So if you plug in a 2, that's going to give us -5/2. If we plug in a 4, we get 7/4. -2 would give us a -5/2, and -4 would give us 7/4. So if I put those together, then now the picture looks like this. And so if I graph it, excuse me, if I graph it, then my line is going to get closer and closer to the asymptote here, and closer to the asymptote here. And then also notice that, okay, so then that's what's going to be our graph. Okay. So that was problems from 2.6. Now we're going to go back to the earlier section. So we'll start with 2.1. So it says write the quadratic function in standard form, identify the vertex, axis of symmetry. So the first thing that I like to do is separate my terms with x's in them, and I leave my constant by itself. And then we're going to take, we want to make sure that the number in front of x squared is a 1. Since it's a 2, we're going to factor out the 2. So if I factor out a 2, I get 2 times x squared plus 4x. And you want to make sure that if you were to multiply the 2 in here, it's going to give you your original problem. Once you factor out that number, then we're going to take half of 4. So half of 4, and then we're going to square it. So half of 4 is 2, and if we square the 2, we get a 4. So this 4 is what we're going to add and subtract into the parentheses. And we can do that because essentially what we're doing is we're just adding a 0 to the problem. 4 minus 4 is 0. What we want to do next is we want to get rid of this -4, or in other words, we want to remove it from the parentheses. And so if I do that, if I bring it down, whatever I get out of this parentheses, it's attached to this coefficient of 2. So I need to multiply the 2 times the -4, and that's going to give me a -8. Okay, so now inside of the parentheses is left with something that we can factor. And so this factor would be x plus 2 times x plus 2. And notice that they're the same. And then -8 plus 7 is -1. Since they're the same, then we can write it as x plus 2 squared. And then this is going to be your quadratic function in standard form. Now from here, we can take the vertex. So the vertex is going to be the opposite of what we see in the parentheses, so -2, and then our k, which is -1. And then the axis of symmetry is always going to be your x-coordinate of the vertex, in this case -2. So the majority of the chapter 2, or the goal of chapter 2, was to find these zeros. And so we're going to go ahead and find a 0. Whenever you're doing these problems, if you can factor out any t's, in this case they're t's, this should be f of t. If you can factor out any of the variables, then you want to try to do that. So for example, here I can factor out a t squared because t squared is part of all the terms. So I worked out this problem a different way, but I'm first going to show you really quick that factoring out what you can is actually a lot easier and faster. So if you factor out a t squared, then the t to the fourth would give you t squared. And if we factor out t squared from the t cubed, then we're going to get a negative t. And then if we factor out t squared from negative 30, from the term negative 30t squared, then we get negative 30. Okay, so in this problem, if you notice, I have two factors, so I can set each one equal to 0. Yes, it's in our opinion, Ruben, Mr. Carizales, and I, we think it's the best. It's a lot quicker, but if you're not sure how to factor, then that's okay because we have other methods, right? So here, now we can try to factor this. So we get t and t. Since I have a negative 30, I should have a negative and a positive. And then two numbers that I can multiply together to give me 30. There's a lot of them. 1 times 30, 2 to 15, 6 and 5. So I'm going to use 6 and 5. And then I can set these equal to 0. And so my answer would be negative 5 and 6. And then over here, if we take the square root, we get t equals 0. And your degree is 4, so that means you should have 4 zeros. So we have 1 here, 1 here. And this, since we're taking the square root, will produce a double 0. So now we have our 4 zeros. Okay. So again, if you are able to factor at the beginning, then I encourage you to do that because it does save time. If you try for a minute and you can't factor it, then we can move on to a different step because sometimes it's not factorable. Okay. But if it has the greatest common factor, then you can factor it out, see if it makes the problem a little bit easier. So I'm going to work it out differently. So let's use another way to do this. Oh, I guess I did do the factoring. So let me go ahead and just click through it. Let me go back really quick. So once you found your zeros here, you want to know if they touch or cross the x-axis. Since the 0 repeated an even number of times, it has an even multiplicity, then it's going to touch and turn. And then for 6 and negative 5, it's going to cross. And so if we were to graph this, you could tell here at 0, the graph touches and turns. And at 6 and negative 5, it's going to cross. Okay. So in a little bit, I'll show you an example where we don't factor something out. Another thing that we want to know is the end behavior. And so I always tell my students, if you remember the written rules for this, always think of these 4 parent functions. If you have an even degree and a leading coefficient is positive, then the graph is always going to have the same behavior as x squared, which is it rises right and rises left. If it's a negative leading coefficient with an even degree, then it's going to fall to the right, fall to the left. If it's a positive leading coefficient with an odd degree, then it's going to rise to the right, fall to the left. And if it's a negative leading coefficient with an odd degree, it's going to rise to the left, fall to the right. So if we look at this example, my degree is odd. So that means that it's either going to be this option or this option. I have a positive leading coefficient. So the behavior for that is going to be that the graph rises right and falls left. And then again, for the zeros and the multiplicity, if your zero is repeated an even number of times, then it's going to touch and turn. Here, my zero is repeated 3 times, which is an odd number. So it repeats an odd number of times. it's going to cross, and it's just going to cross through the x-axis. Okay, so the next thing we want to cover is the possible rational zero theorem test. And this is going to be helpful in creating a list of numbers that we can check to see if they are zeros. And that avoids us from checking an infinite amount of numbers. In order to do this, we're looking at two things. We want to find the factors of the constant term, which is the number that doesn't have a variable. And we want to find the factors of the leading coefficient, which is the number in front of the variable with the largest power. Okay, so we look at this problem. We're going to find the factors of 9. So the factors of 9 are 1, 3, and 9. And then the factors of 1 is 1. But we can also have -1, -9, and that would still give us a 9. So we're going to consider the plus and minus 1, plus and minus 3, plus and minus 9, all divided by the plus or minus 1. So 1 divided by 1 is 1, 3 divided by 1 is 3, and 9 divided by 1 is 9. So when you enter your answers, WebAssign, you want to enter from smallest to greatest, and they don't have the symbol for plus or minus, so you'll need to enter them separately. So here are my possible zeros. And so now we want to check from that list. So we're going to check from this list if any of them are actual zeros. And so I always like to start with 1. And so here, let's check. We have 1, 1, -9, and -9. I'm going to bring my 1 down. 1 times 1 is 1. 1 plus 1 is 2. 1 times 2 is 2, plus -9 is -7, times 1 is -7. So we end up with -16, which doesn't work. We didn't get that 0. So that tells me this is not a 0. So then I'm going to try -1. So we do the same process and we get the 0. So now we do the same process and we get the 0. So now we can help Mr. Carizales have a happy face. Since we get a 0 here, then that means that -1 is a 0. But more importantly, what it helps us to do is to work with something that is more familiar. So we can take the result here, get the quotient, so we get x squared minus 9. And now this is quadratic, so you have options. You can try to factor, or you can try to use the quadratic formula. In this case, I can use the square root property and solve for x. So I end up with plus or minus 3. So my zeros are -1, -3, and +3. My factors are x plus 1. To get the factors, we just take the numbers, the constants, to the left side, and that's going to create our factors. So let's do a problem where we have to do everything. So here we have x to the 4th minus x cubed minus 6x squared. Again, if you can factor out the greatest common factor, then you want to go ahead and do that. I'm going to solve it using a different method. So here, oops, let me go back. So I'm going to use the rational zero theorem. My constant is 0. So, and my leading coefficient is 1. So I'm only going to have a possible zeros of 0. So I'm going to test 0. So if I bring 1 down, so let me just explain this part here. We have a 1 for the x to the 4th, -1 for x cubed, -6 for x squared. We need to use a 0 for x and then a 0 for the constant term. So if I bring down the 1, I get 0. -1 times 0 is 0. -6 times 0 is 0. And then 0 plus 0 is 0. So my quotient is x cubed minus x squared minus 6x. So I can repeat the process. But again, if you factor out a greatest common factor, it might make it easier and faster. But I'm going to go ahead and just continue the process. So we have 1, -1, -6, and 0. Again, I don't have a constant, so if I find the possible zeros, I'm going to end up with 0 again. And so if we plug in everything here, we get the following. So my quotient is x squared minus x minus 6. Now it's quadratic, so you can try to factor, or you can use a quadratic formula. And this is going to factor, but I think I used the quadratic formula just to show you a different method. So if you use the quadratic formula, then you end up with x equals 3 and x equals -2. But at the beginning, you could have just factored, and it's going to give you the same solutions. So my zeros are 0, 0, -2, and +3. So whenever we graph this at 0, it's going to touch and turn. At -2, it's going to cross. And at 3, it's going to cross. Determine the maximum number of turning points. So we can do that by taking the degree n and subtracting 1. So we have at most 3 turning points. Give me a second. I lost my page. Where did I go? Okay, here we go. So if we continue, the first thing you want to do is plot your points. So these are my points, -3, 0, and -2. Then we're going to apply the end behavior. So the end behavior, we have a degree 4, which is even. And then we have a positive leading coefficient. So the behavior for this is going to be that it rises to the right and rises to the left. At this 0, it's going to cross. So I just kind of sketch it through. And at this 0, it's also going to cross. So now I need to fill in the gaps, right? So to do that, we're going to choose additional points. So we can get points from anywhere. But if I pick a point over here, it's not going to be as helpful. If I pick one over here, it's not going to be as helpful. So I want to fill in the gaps in between my zeros. So let's pick some points. So I chose a -1. So if I plug in -1 here, I end up with -4. I also chose 1. So if I plug in 1, I get a -6. And then I pick 2. So 2 will give me a -16. And you could barely see my points right here. So if I continue my graph, then I can sketch my graph. This is going to come up. It's going to touch at 0 since I repeated an even number of times. And then it's going to come down. Okay. So on WebAssign, they usually give you a multiple choice for you to pick your graph. I encourage you to draw it on paper and then compare with your options. So in this example, the graph would look something like this. So I think I did pretty good. This would look like this one. That's my answer. And let's continue. So now we have find the polynomial function with the given information. So now what they want us to do is find the actual equation. And here I know that this is degree 4. They give me 3 zeros and then give me a solution point. So let's look at our zeros closely. So we have x equals -4, x equals 1, x equals I. Since I have degree 4 and I have a complex 0, then the conjugate is also a 0. So I can include x equals -I as one of my zeros. So here I'm going to need my factors. And so I can write these as x plus 4, x minus 1, x minus I, and x plus I. So I can set up my polynomial. And then what you want to do is multiply it out. So you can multiply these together first if you want to, but I like to multiply the imaginary numbers first. That way we just get rid of them. So x times x, and you can use the shortcut, right? Since they're conjugates. If you're not sure of the shortcut, then you can just do what I did here. X times x, x squared, x times I, ix, negative ix, and then we have a negative I squared. So the ix's will become 0. And then I squared we know is the same as -1. And if we simplify, then we have x squared plus 1. So now we're going to multiply the next two factors here. So x times x squared is x cubed, x times 1 is x, negative 1 times x squared is negative x squared, and negative 1 times 1 is negative 1. Combine any like terms that you might have, and then we're going to multiply times x plus 4. So x times x cubed is a positive. Let me see what happened here. Okay, so x times x cubed is x to the fourth, and then x times x will give you x squared, x times negative x squared will give you a negative x cubed, and then x times negative 1 would give you a negative x. 4 times x cubed would be 4x cubed, and then 4 times x is 4x, 4 times negative x squared, and 4 times negative 1 is negative 4. So now we can combine like terms, put them in order. So we have x to the fourth. Then I have a negative x cubed plus a positive 4x cubed will give me a 3x cubed. And then I have an x squared plus a negative 4x squared would give me a negative 3x squared. I have a negative x plus a 4x will give me a 3x, and then we have our negative 4. So now we can use our solution point. So in your solution point, when x is 0, your result is negative 8. So for f of x, we can put negative 8. Anywhere you see an x, we're going to replace it with 0, and then we're going to simplify. So all of this is 0, so we get negative 4 divided on both sides. So we get that our leading coefficient here is going to be a 2. So we plug it back in. We get f of x is equal to 2 times all of this polynomial. And last, we just distribute the 2 in the parentheses, and we end up with 2x to the fourth plus 6x cubed minus 6x squared plus 6x minus 8. And so if you were to find the zeros of this polynomial function, then this would be the zeros for it. So we just went backwards. Okay, and now I believe this is going to be the last problem. Excuse me. So here it says use the given zero to find all the zeros. And the only thing they give you is that 4 plus 2i is a 0. Okay, so since it's a 0, then we know that if we were to apply synthetic division, it better give us some remainder of 0. Okay, so let's see if that happens. So we have x cubed is 1, x squared is negative 12, x is 52, and then we have negative 80. Then I have 4 plus 2i is my 0. So I'm going to bring down my 1. And 1 times 4 plus 2i is 4 plus 2i. Plus a negative 12 gives me negative 8 plus 2i. So now I'm going to multiply negative 8 plus 2i times 4 plus 2i. And we end up with 4 times negative 8 is negative 32. 4 times 2i is 8i. 2i times negative 8, negative 16i. And 2i times 2i is 4i squared. So it looks like we're just making it look crazier, but it's going to clean up in a little bit. Let me go back. So I squared is the same as negative 1 times 4 is negative 4, plus a negative 32 is negative 36, and then 8i minus 16i is negative 8i, right? So negative 32 minus 4. Let me clean it up. So now we're at negative 36 minus 8i. If I add the 52, then I get 16 minus 8i. So then I need to do that again. So we're going to multiply 4 times 16, 4 times negative 8i, 2i times 16, and 2i times negative 8i. And then we get this information here. So I squared is the same as negative 1, so we would replace that. And if I simplify, then I get So -1 times that is 16. And then 64 plus 16, hopefully it's 80, which it is. And then -80 gives me 0. So all I did was I just showed that 4 plus 2i is a 0, which they already told me it was, right? But more importantly, what I was trying to do is break down our cubic polynomial to something that's quadratic. So here I have a 1 for x squared. -a plus 2i is my coefficient for x, and then 16 minus 8i. So wow, it's quadratic. So now it looks a little weird because it has those imaginary numbers, but that's okay. We're going to do the same thing. So let me go back. So since 4 plus 2i is a 0, that also tells me that 4 minus 2i is also a 0. So now I'm going to do the same process, but now I'm going to use 4 minus 2i. So my quotient here had an x squared, that's a 1. The coefficient for this is going to be -8 plus 2i. And then my constant is 16 minus 8i. So I'm going to bring down my 1. 1 times 4 minus 2i is 4 minus 2i. -8 plus 4 is -4. 2i plus -2i is 0. And then I'm going to multiply 4 times -4 is 16. 2i times -4 is positive 8i. And I get the 0, which is good. So now let's look at the quotient. So since my quotient was x squared, now this 1 is going to be an x, and then I have -4. So now I can solve x minus 4, right? So I'm going to put x minus 4 is equal to 0, so x is equal to 4. So what are our zeros? X equals 4, this should be a 4. Okay, so it's not x equals 0, it's x equals 4, and then we had our 4 plus 2i, and our 4 minus 2i. And so that would be our zeros. Aren't these fun, guys? These are exciting, right? So that was just a little bit of each of the sections that are part of your exam 2. And so if you want a copy of this presentation, you can download it. There's a box, if you see my mouse here, there's a box with an arrow pointing down. Just click on that and it will let you download the whole PowerPoint. And then throughout the session, I saw the links for our YouTube channel. If you want to come back, maybe your test is after spring break and you want to review when you come back, then this presentation will be available for you to go back and view it. You can slow me down, you can fast forward me. So that's the beauty of videos, right? But I want to wish you all the best on your exam 2. And I want to wish you a happy spring break. And then Mr. Carizales, I don't know if you if you have questions, we still have time so we can work something out for you as well. If not, then I'll pass it back over.
Thank you, Ms. Chuka. I just wanted to add one more thing since we still have a little bit of time. You might also have some questions that ask you to write your polynomial as a linear factors. So, and this is a great example that we can do. This is on this last problem. Since Ms. Chuka gave us the zeros here, we can see that we can have the factors of these. So if we were going to write the polynomial as linear factors, we have them right here. And again, remember, when we're talking about linear factors, is when our degree of our x is, or our exponent is the highest is a 1, okay? And then Ms. Chuka's fixing that 1 for our 0. So again, this is a great way also to get our factors for a polynomial, okay? So again, thank you all for joining us. Thank you, Ms. Chuka. Everybody have a great spring break.
Thank you, Ms. Chuka, for your wonderful presentation, as well as to Mr. Carrizales. We do want to remind you all about your previously recorded sessions, which are available on YouTube playlist. Today's session will also be available on the playlist later on today. Also linked is a short survey to help us improve our TVE sessions. Please take time to fill out the survey. Before you all leave, I want to share the TV sessions that we will have not next week. Don't forget. Enjoy your spring break. We will be back on the Friday, March 22nd. On that day, Math Happy Hour will be covering Math 1314 with exponential and logarithmic functions. And Math 1324 will be covering systems of equations. For that day, Student Success will be presenting the Prep to Rank program. And then later on today, if you could please join us with the Student Success, and the topic will be EPCC publications. Again, thank you all for coming in today. Have a great and safe spring break. Not only a weekend, but you guys are going to have a whole week, all of us. If you guys have any questions at this moment, feel free to use your chat box or your mic. We hope to see everyone again for Happy Math Hour.